Hi everybody, I'm going to go ahead and get started. Thanks again for joining us. My name is Allison Alcott and I've been working at RockWare as a trainer and a consultant since 2000. Let me get this PowerPoint going here. During the next 20 minutes, I will quickly give an overview of the stratigraphy modeling tools available in the Borehole Manager portion of the RockWorks15 software. This outline shows the sequence in which the information will be presented. Please feel free to type your questions into the GoToMeeting chat box at any time, and we'll either answer them during or after the presentation. So here we go. The first thing I want to talk about is how stratigraphy data would be stored in the Borehole Manager database in the RockWorks15 product. So I'm going to first display a view of the stratigraphy data for a single borehole. As you can see here, the top and base depths for each stratigraphic unit are stored in the stratigraphy table, and this table links to what we call a stratigraphy types table that looks like this. The stratigraphy types table is basically just a reference table that stores formation names, patterns and colors, the order of the units, and a few other types of information. Now I'm going to bring up the RockWorks program and just give you a quick overview of what the Borehole Manager interface looks like. So you should all see the RockWorks program now, and for those of you who are not familiar with it, we have a project manager over here on the left side of the screen, and we always display our project dimensions at the top of the screen. And these are important because they govern the extents of any map that you would create, as well as the extents and spacing of any grid or solid model that you create. So it's important to establish appropriate project dimensions before you get started. I have a list of boreholes within my project right here, and notice that as I click on different boreholes that the display changes over here. So that's how I access different data for different boreholes, is just simply by clicking on the borehole in this panel. Here we're displaying location information for each borehole or well, so that the most important information for your location data is the name of the borehole, easting and northing coordinates for the collar of the well or the borehole, the collar elevation, and the total depth. If I click on the stratigraphy table right here, this displays the stratigraphy for whatever borehole is selected in this panel. And if I click on this button right here, it takes me into that stratigraphy types table. And again, this is really a reference table that lists patterns and colors associated with each formation within your project. So I'm going to go back to the PowerPoint presentation now and move on to a discussion of the differences between lithology and stratigraphy. There are significant differences in how lithology and stratigraphy data are modeled, so it's important to be sure that you're using the correct database table and modeling tools for your data. I typically describe lithology as your observed material type, and this could be rock or unconsolidated sediments. For example, if you're logging a hole and you observe a 10-foot section of interbedded sands and silts, you would probably log that detail in the lithology portion of the database. Stratigraphy, on the other hand, is your correlated units or your geological formations. These are often groups or packages of lithologies that can be correlated across at least some of the project area. I've found that one of the easiest ways to describe the differences between the two data types is to view a cross-section, so I've displayed some here. The top cross-section shows a modeled lithology cross-section, and the bottom one is a modeled stratigraphy section. And you can see that the lithology section shows a lot more detail and has a much blockier look than the lower stratigraphic cross-section. These differences are mainly due to differences in the way that the two data types are modeled by the program. Here I've displayed lithology and stratigraphy block models, and again the difference in how the two data types are modeled is pretty striking. I'm going to focus on stratigraphy modeling for the rest of the session, and we actually have an online webinar covering lithology models scheduled for November. The next thing I want to cover is how the program creates these stratigraphy models and how it stores them in your project directory. So first of all, a stratigraphy model is composed of a series of stacked gridded surfaces as illustrated in this image, this upper image on the slide. When the program displays the stratigraphy model in 3D, we add side panels to fill in the gaps between the contacts, and it's displayed as the image as shown in the image below. RockWorks offers numerous grid interpolation algorithms. I think that most of our customers use triangulation, kriging, or inverse distance to create these stratigraphic gridded surfaces. Now this point that I'm making here is something that I think a lot of our customers it's something our customers are not aware of, so I think it's an important point to make. When a stratigraphy model is created, RockWorks actually creates and stores grid files in your RockWorks project directory. And this is an example of what they would look like if you were to view them using Windows Explorer. So if you used Windows Explorer to open up your project folder, you would see grids that look like this. As you can see, RockWorks is systematic about assigning names to these grids, and these grids can be used in other parts of the program as well once your stratigraphy model is created. So you could create a contour map of one of these gridded surfaces, or you could use one of them to constrain a solid model of lithology or some other sort of downhole numerical information. The program creates top and base grids for each stratigraphic unit, as you can see here. And if you've told the program to hide the thin zones, which basically just renders a unit transparent when the thickness of the unit falls below a user-defined cutoff, then the program also creates a top and a base grid with the word clipped attached to it. So typically the program is actually going to create 4 grids for each stratigraphic unit when a stratigraphy model is created. Once these grids are created and stored in your project, you can tell the program to use these grids when creating a stratigraphy diagram rather than going through the process of reinterpolating the grids every time you want to create a diagram. What's nice about this is that if the automated tools in the Borehole Manager just don't work for you, let's say that you want to use one interpolation method to create for one surface and another interpolation method for another surface, you can actually manually construct these models simply by placing grids in your project dimension, in your project directory that have the appropriate names. And these grids can be created, say, in the RockWorks Utilities part of the program, or they could even be pulled in from another program like ArcGIS or Surfer. The key here is to use the appropriate naming convention so that the program correctly classifies them as stratigraphic contact grids when it's creating a stratigraphy diagram. So next what I want to do is just jump into the program and show you the steps that you would take to create a stratigraphy model through the Borehole Manager. So I'll open up RockWorks again, and I'm going to go to the stratigraphy menu and I'm going to choose Model. Just because creating these grids can be somewhat time intensive, I'm going to use grids that are already stored in my project directory to display a model. So I have this Interpolate Surfaces option checked off. If you're creating a stratigraphy model for the first time, you would want this to be checked on. So I'll click on the Process button. And the program is now looking through my project directory, looking for those appropriately named grid files, and then using those to construct a solid model or a block model of your stratigraphy. And this is what that block model would look like. This is being viewed in our RockPlot 3D viewer. And you can see that you can rotate the model, you can zoom in and out. We have a data tree over on the left side of the model that allows you to turn different items in the 3D viewer on and off. Before I get into some of the ways that you can manipulate the way this model looks, I want to go through some of the options you have when you're creating a model. So I'm going to jump back over here to the left menu options. If I click on the little plus sign next to Interpolate Surfaces, these are all gridding options basically that you can specify when a model is being created. If I click on the gridding options button, it opens up this window. And this right here is probably a webinar in itself. It's just going through all of the different options available for gridding in RockWorks. So I'm not going to get into these, but if you're interested in us covering those in a future webinar, send us an email and let us know, because we're interested in knowing what people want to learn about. If you have a detailed topographic grid that shows, for example, more detail than what would be reflected in a grid created just based on collar elevations of your boreholes, then you can actually load a grid surface into the program and tell it to use that as the top surface for your model. So especially if you're in a mountainous region or any region that has a little bit of topography, or if you're in an area that's maybe been modified with a pit or some other sort of man-made features, then using this tool would be really important because it'll actually allow you to use one of these externally created grid files to clip the top of your model. You can actually also use a grid file to clip the base of your model as well. So if, say, you have kind of a planned excavation and you want to predict what kind of materials you might encounter during the excavation, you could actually clip a model from below as well, and that would just give you volumes of potentially excavated material. We have an option to use a polygon filter on your model. So if you want your model to only fall within, say, a user-defined lease boundary or property boundary, then you can do that. You can use a polygon to limit the extent of your model. And when you do that, then your model will have an irregular boundary shape rather than this nice rectangular shape that you see with the model that we're looking at right now. And then the base plate option actually allows you to specify a flat boundary for the bottom of your model. In this example, we're just having the bottom of the model. Let me turn off the perimeter cage. The bottom of the model really just follows the bottom of your boreholes. But if you wanted it to be a flat boundary, then you would use a base plate. So moving on to some of these diagram options, the explode option, which I'll show you an example of in a slide, will basically just add space between your units when it's visualizing the units. This hide thin zone actually, and I mentioned this in the last slide, but what that does is it renders a unit transparent when it pinches out. So if you have units that come and go, then turning on this hide thin zones option is a good idea. And then we of course have the option to plot logs or plot this reference cage around your model. So what I want to do next is talk about how you can turn different units on and off and even manipulate the way that the units are displayed in a model. So I'm going to turn off every other unit and just focus on these two. Let's say they're aquifers, so this upper yellow aquifer and this lower orange aquifer. Each aquifer is actually composed of top and base grids and side panels, and these components can actually be turned on and off. So I could say turn off the top grid if I wanted to. You can see now that the top of the unit isn't displayed. I can also turn off the side panels if I want to see through the unit. So I turn the side panels off and now you can see right through it. You can also manipulate the manner in which the gridded surfaces are displayed. If I click on the plus sign next to this top unit, then I can actually choose this elevation grid, and I can modify the color scheme for the elevation grid. Say I may want to use some sort of color scheme to display the surface rather than just a solid color. I can also modify the draw style. I'll choose wireframe, and now I can actually start seeing the grid cells within the surface, within the gridded surface. I can also add transparency to the surface if I want to. So I'll make the opacity 50%, and now I can start seeing through the surface. Just so you know, you can also add transparency to groups of objects in the 3D viewer. So if I were to just select this lower unit, the Potosi Formation, right-click on it and choose Options, I could add an opacity to this as well so that you can see through it. And that applies to really any object in the 3D viewer. You can apply it to strip logs, three-dimensional plumes if you're creating them, images. So that transparency attribute is really kind of a global attribute in our 3D viewer. All right, so I'm done with that. What I'm going to do now is jump back to the PowerPoint presentation and move on to the next topic, which is visualization of these stratigraphy models. We've talked about how you can view them in 3D, but let's now look at how you can actually start slicing and dicing through these these stratigraphy models once they're created. In this slide, by the way, this is a view of an exploded stratigraphy model. So I talked about the explode option when I was going through those menu options, and if I had turned that on, then you would get a model that looks like this. This is a list of different ways in which a stratigraphy model can be displayed, and I'm going to go through now a few different slides that give examples of what these diagrams look like. This is an example of a stratigraphy profile. When a profile is created, the user draws a straight line on a map, and the program displays the stratigraphic contacts along that line. It also projects boreholes that fall within a user-defined distance away from that line onto the diagram. So if you look at the map displaying the profile line at the bottom of the slide, you can see that there's a yellow box around the profile line, and the boreholes that fall within that yellow rectangle are plotted on the diagram. This is an example of a stratigraphy section, and it looks very similar to a profile, but as you can see in the lower map, the cross-section line goes from hole to hole rather than following a straight line profile. So for a cross-section, the user really uses a polyline to define the section rather than a straight line, rather than the straight line that they would use for a profile. This is an example of a stratigraphic fence diagram. And fence diagrams are basically just a series of sections or profiles displayed in 3D. And in this example, we're displaying 3D stratigraphic strip logs along with the fence diagram. This movie of the rotating fence diagram was exported from the RockPlot 3D viewing engine, which also includes options to export 3D DXF files if you wanted to load it into a CAD program, 3D shape files if you want to load the fence diagram into ArcScene, and we also have some Google Earth exports. So you could take this this fence diagram into Google Earth and hover it above the ground surface as well. This is an example of a plan map, and plan maps and surface maps are basically just show you the intersection of the stratigraphy model with a horizontal plane or a grid. And in this case, we're showing you a 2D map of the stratigraphy encountered at a user-defined elevation. So that's really what a plan map is. It's stratigraphy at a specific elevation. A surface map would look similar to this, but it would show the stratigraphy encountered along a grid with varying elevations, such as a water table or a planned mine floor. Before proceeding, I'm going to go back to the program, and I'm going to show you the steps taken to create a stratigraphic cross-section. So now that we're back in the program, and I'll go to the stratigraphy menu, and I'm going to choose Section and Modeled. Again, notice that I have the option here to interpolate surfaces, and if I have that checked off, the program's just going to use gridded surfaces stored in my project directory to construct the diagram. I'm going to turn on a stratigraphy legend. I'm going to tell the program to plot some logs. If I click on this 2D strip log designer right here, this governs the layout of the strip logs that will be included in the cross-section. And then I can go to this section selection map window. And if I'm creating a cross-section for the first time, I'll probably just use my mouse to draw a cross-section line that connects the dot from hole to hole. But keep in mind that once you've created a cross-section, you can save this section line with a specific name, like Section A or Section B, and you can pull it up later, so you don't have to redraw these cross-sections every time. I'll click on the Process button. And the program will create the cross-section for me. So the steps that you would use to create a profile or a fence diagram or even a plan map or a surface map are very similar. It's a very similar interface, especially if you're choosing, if you're specifying the line of the cross-section or the profile. All right, so now I'm going to go back to the PowerPoint and talk about some of the volumetrics tools available in the program. Now, first of all, when you're viewing a model in RockPlot 3D, you can actually view the volume and the mass of individual units in the data tree to the left of the model view. And this is something I should have pointed out when I had the model open. In this image, I've circled the display of the volume and the mass for the specific unit. This type of estimate is grid-based, so we're simply estimating a unit thickness based on the top and the base elevation grids, and then we're multiplying that thickness by the area of the grid cells, and then we're just summing everything up. So it's a simple grid-based volume calculation. And keep in mind that this volume would be for the volume of the entire model. It would be the volume of a stratigraphic unit covering the extents of the entire model. So RockWorks also includes tools for calculating volumes based on user-defined intervals, and these tools output tabular reports that can be easily exported to Excel and then incorporated into reports if you need them to. Just keep in mind that these reports cover the volume of each unit that is encountered over a specific elevation interval. So what I'm going to do next is switch back to the RockWorks program and show you the steps that you would take to create one of these reports. If I go to the Stratigraphy menu, I'm going to go down to these volume options. And we have an option to create a volume based on a solid model as well. When you're creating a stratigraphy model, you can convert it to a solid model composed of blocks if you want. Because that type of volumetrics estimation is a little bit more time consuming, I'm just going to stick with the grid-based estimation. When you're setting this report up, you specify a top elevation and a base elevation and then an interval. You can tell the program to display both volume and mass, and then these options all have to do with just kind of the aesthetics of the report, annotations and things like that. I'll click on the process button and the program will just generate this report, and again it can be saved as a tab file that can be opened up in Excel. You can copy and paste this from this program into Excel as well. So once these reports are created, you can get them into, kind of a pretty table format for your reports. All right, what I'm going to do next is move back to this PowerPoint and talk about how you would deal with pinch outs when you're creating a stratigraphy model. Keep in mind that RockWorks is really designed to model continuous stratigraphic units, but if you do have a unit that pinches out, then there are definitely ways to deal with it in the database. I'm going to give examples of two types of pinch outs. The first type of pinch out would occur when a unit pinches out completely between two other units. And in this example, you can see that this light blue unit, unit C, pinches out on the left side of the profile in between units B and units D. The best way to deal with this is to list the unit in your database as existing, but with a thickness of 0. So that's what I'm displaying right here. I'm displaying the stratigraphy data for drill hole 3, where unit C is missing, and you can see that I'm using the same depth to top and depth to base for unit C. And that depth also matches the base of unit B and the top of unit D. This just gives the program more data to work with, more control when it's creating these gridded surfaces, and you'll get a much more accurate stratigraphy model if you take this approach rather than just not listing the unit at all when it pinches out. The second type of pinch out would be where a unit, most likely a lens of some sort, exists within another unit. So in this example, you can see that unit C exists within unit B, but only in specific boreholes. First of all, if you have a lot of these that can't necessarily be correlated from borehole to borehole, then you should really use the lithology modeling tools within RockWorks. But if you absolutely have to use stratigraphy modeling, say you prefer the look of the stratigraphy diagrams versus the lithology diagrams, and if you truly can correlate these units from hole to hole, then the approach would be to break unit B up into two units, unit B1 and unit B2, and then have unit C come and go, depending on whether it exists or not within your database. Again, as with the approach previously described, for example, in unit DH03 where unit C does not exist, you would still want to list it existing in the database, but with the same depth to top and depth to base values. The last topic I want to cover is what you might do if you've created a stratigraphy model in the program and it's not quite right. Especially when you're dealing with these pinch outs, sometimes you can get a model that looks pretty good, but you still might want to make some tweaks before you say where to present it to a client. And what I'm going to do is open up the example that we've been using before and just take another look at that light blue unit that pinches out. So I'm going to zoom in here, and I'm going to turn off these upper units. And I'm actually going to turn off this Leadville limestone unit, or Unit C, as well. And what I want to do is look at the distribution of the unit in the project. Now, if I were to, say, hand draw where I might estimate this contact to be between where this unit exists and doesn't exist, I would probably draw it, right through the middle, right here. I'm tracing the area with my mouse. If I turn the unit back on, you can see that the program has done a decent job. It's in the ballpark range of where you might place that contact, but it may not be perfect. There are tools in the program that allow you to take the grids created by the Borehole Manager and edit them, and then reconstruct the model using your edited grids. And this is not something I can cover in this class or this webinar, but what I wanted to do was bring up a case study on our website that will point you towards tools that you can use to manually modify these models. So I'm going to start on our Rockware page, and if I go to the main RockWorks page, web page, over here on the left side of the screen, there's an option to, under support, to look at a series of different case studies. And if I click on the stratigraphy case study, there are actually two here that are really useful, but what I wanted to open up with is this one that specifically focuses on editing models that have been created in the Borehole Manager. So this is an example of a model that has been created with the Borehole Manager that has a lot of units pinching out across the surface of the model. The case study talked you through steps that you would take to convert a model that looks like this to a model that looks like this. And it's really just done using a series of steps with grid math, maybe some grid filters that are applied to isopack grids, and also using some polygon clipping tools. So just keep in mind that if you have more complicated situations, that you can modify a model that's been created in the Borehole Manager after the fact to look a little bit prettier. All right, and back to PowerPoint. What I wanted to do is just leave you, leave you with this slide. And first of all, keep in mind that if you do have a more complex stratigraphy model that you're getting started on, feel free to send us your data. We're happy to take a look at it and give you some suggestions on how to approach the modeling process. And then I just wanted to leave you with some additional information about how to get in touch with us and get more information about RockWorks. We're working on more and more how-to videos that we're posting on our YouTube channel, and we'll be mentioning these in our monthly announcements as we post them. Our next in-house workshop, which is held in Golden, Colorado, is scheduled for late January. Also keep in mind that we're always available to schedule custom online training sessions, and these are becoming more and more popular. Thanks again for joining us. That's all, and we'll go ahead and take questions now if anybody has any.